Hi everyone, I'm happy to be here to present our work, PolyMaX General Dense Prediction with Mask Transformer on behalf of our Google research team in WACV. Dense prediction, including segmentation, depth estimation, and surface normal, are important vision tasks since it can enable various real-world applications. Conventionally, people tackle this problem by formulating them as per-pixel prediction, specifically assign a predicted value to every pixel. When the assigned value is discrete, such as class index for segmentation, the task is constructed as per-pixel classification. If the target outputs of the problem are continuous, such as depth and surface normal, they are cast as per-pixel regression problem. Recently, we are witnessing a paradigm shift from per-pixel classification to cluster prediction. Inspired by the object detection network data, Mask DeepLab and Mask Formal proposed to classify each segmentation mask as a whole instead of pixel-wise. They build upon the mask transformer-based model. The key is the transformer decoder will generate cluster centers by iteratively updating a set of learnable embeddings. The generated cluster center embeddings are multiplied with the pixel features to yield a set of binary masks. This procedure groups pixels with similar semantics into the same clusters. That's called pixel clustering. The other component is the cluster classification, which assigns cluster label to each cluster with the probability distribution over all classes. In summary, the cluster prediction paradigm has two steps. The first one is pixel clustering, which groups pixels into a set of clusters, and the second one is cluster classification, which assigns semantic labels to each cluster with a probability distribution. Now, let's look at how to transform depth estimation to cluster prediction paradigm. The main difference of depth estimation from segmentation is the continuous output space. Fortunately, DORN, the previous work, and other previous work demonstrate the potential of discretizing the continuous depth range into a set of fixed bins. By performing classification among a set of depth bins, it shows promising results. After casting the depth estimation task into classification, it now fits nicely into the aforementioned cluster prediction paradigm. This insight of using classification to perform dense prediction in the continuous domain opens up the possibility of performing many other continuous depth prediction tasks using the cluster prediction paradigm. So we want to look into the question, can we extend this cluster prediction paradigm even further to solve many other continuous depth prediction tasks? We use surface normal as a representative example to show how to generalize the mask transformer-based framework to other dense prediction tasks, since this task has a multi-dimensional continuous output space. For example, the definition of surface normal problem is for each pixel, the problem aims to learn the direction that is perpendicular to the tangent plane of the corresponding point in the 3D world. So the output space is three-dimensional, continuous, and from the geometric perspective, it tries to map from the 2D image to the 3D points on the surface of a unit 3D board. So from this geometric meaning, we can partition the surface of the unit board to different regions, in other words, different clusters. Here we illustrate an example of 4 clusters to explain how we can fit the cluster prediction paradigm. We jointly learn the 3D unit vector of the 4 cluster centers with the corresponding probability maps. The 4 probability maps, the colorful maps here, represent the predicted probability distribution across different vector directions, such as the right-facing, left-facing, downwards, and upwards. The probability maps are linearly combined with their corresponding 3D unit vector to produce the final continuous surface normal map. Now, here is the overview of our proposed PolyMaX architecture. So we propose PolyMaX to unify the dense prediction task with the mask transformer framework, where cluster centers are used as an intermediate representation. The mask transformer framework contains two paths. The first one is the pixel encoder-decoder to generate per pixel embeddings, and the second one is the transformer decoder to generate cluster centers from input queries. The prior distribution map is generated by first multiplying the per pixel embeddings with the cluster centers, followed by a softmax operation. For semantic segmentation, the final segmentation map is obtained by applying the augmax operation to find the maximum probability semantic label. For depth estimation, we further apply another MLP to estimate the bin center values, which are then linearly combined with the probability distribution map to form the final depth map. Similarly, for surface normal prediction, the estimated 3D unit vectors are linearly combined with the probability distribution map to form the final surface map, normal map. So we set up our experiments as the following. We use K-Max Deep Lab with different backbones as our model, and we mainly use taxonomy and the NYU V2, these two indoor datasets as our training dataset, and use NYU V2 as the evaluation. So here we found the taxonomy provides a large-scale, high-quality depth and surface dataset with high-quality depth and surface normal ground truth. But unfortunately, the segmentation maps provided in the dataset has low quality, and we will also propose to provide the segmentation labels using our model. We're going to show later. Here is our main result of the proposed PolyMaX model. And we show that this model outperforms all the previous works on 3 benchmarks of the NYU V2 dataset. This even includes the Zoe depth model, which is trained with a combination of 12 datasets, and the diffusion-based VPD model, which is trained with the large-scale Liang-5B dataset. We show the result, the visualization of our model predictions, and our model is capable of resolving fine-grained details and the complex structures, even when the ground truth has artifacts. Here is the scalability analysis for our model with the different data scales. As you can see, when the pre-training data scale is low, then using the per pixel prediction built upon the deep level V3 outperforms the PolyMaX model because the small scale data cannot fully utilize the large capability of our proposed PolyMaX model. But once the training data scale increases, our PolyMaX model scales much better than the per pixel prediction baseline. We also investigated the cluster granularity, and we found the optimal cluster numbers for depth and the surface normal is 16 and 8 respectively, but there is not a significant difference among the different cluster numbers. So we look at the visualization of the cluster representations. Despite the redundancy in the 16 probability distribution maps, which also explains why there is not much difference among the different cluster granularity. These unique ones clearly demonstrate that the pixels are clustered as closest, mid-range, and furthest distance, which validates the effectiveness of our proposed model with cluster prediction paradigm. And similarly, we also demonstrate the cluster presentations for the surface normal model. And lastly, we show the visualization of our produced segmentation ground truth for the taxonomy dataset using our model. We will also release the code base and this dataset soon. And thanks everyone for attending this talk, and also thanks the whole team members and all the contributors. If you have any questions, please feel free to contact us. Thanks.